So hello, my name is Christoph Pettis, and we're going to be talking in this session about practical PostgreSQL indexing. So thank you all very much for dropping in on this talk. First, just a little bit about me. I'm the CEO and lead consultant of PostgreSQL Experts. We're a consultancy based in Alameda, California. If you occasionally hear an airplane go by, that's because we're right near Oakland Airport. This is my email address and my sadly not too often updated personal blog and my Twitter account. I've been doing Postgres for 20 years now. PGX has been around for about 10, and that's what we do. Okay, so on to indexes. So the first rule about indexes is we don't need indexes. How many people out there have read the SQL standard? I can't actually see hands in this, but if you know, the SQL standard doesn't really say anything about indexes. The indexes are an extension to SQL, and an index, if it's working properly and the database system is, never ever changes the actual result that comes back from a query. They're an optimization, and a 100% SQL standard compliant database can have no index functionality at all. You wouldn't like it very much, but it would work. The reason we need indexes is because we don't like this, which is we don't want queries to run in order n. That is to say, we don't want queries to just keep getting slower and slower the number of records they have to process in the table. So, because without an index, all queries are sequential scans at best. That's the best you can hope for. And this is really bad. 250 million row table, if you had to look up one record and scan the entire thing, not great. So the point of an index is to turn an ON index into something better than ON, ideally O log n or log 1, a constant. But just keep in mind, indexes are essential for database performance, but they don't result in speed improvements in all cases. An index isn't guaranteed to automatically speed things up. A very common question on Postgres is, why isn't it using my index? And the answer often is because the index wouldn't help you very much here. It's also important to match indexes to the particular queries and data types and workloads they're going to support. Don't just throw a bunch of indexes into the database and hope for the best. That being said, let's look at the Postgres. Postgres has an amazing set of indexes. So we have a toolbox full of indexes. We have btrees, hash, gist, gin, spgist, BRIN, and bloom indexes. Wow, that's a lot of indexes. It has an amazing and wide range of index support, and it actually has extensible frameworks to add your own. Each index has a range of queries and data types that they work for best. And so the question is, how do you know which one to use? Someone should give a talk on that. Oh, right, that's this talk. Okay, so first let's go through each index type and talk a little bit about its characteristics and what it's good for. First, btrees. Btree indexes. This is one of the most powerful algorithms of computer science, and its name remains a mystery. What does the B stand for? Balanced or broad or bowing or bushy? Was it the one that came after an A-tree index? We really don't know. It's lost in history. B-tree indexes are old enough to be your parent. The first paper was published in 1972 on B-trees. It's the default index time in Postgres, and pretty much every database everywhere uses B-tree indexes. So it's as far as algorithms can ever win, it won. So there's this graphic that describes how B-tree indexes work. Basically, it's a tree structure index with a variable number of, well, either a variable number of or a fixed number of buckets in each of keys in each bucket, and they structure into a range. So, for example, in this graph, everything up to 7 is in the first one, the first leaf. Everything between 7 and 16 is in the second leaf, and everything above 16 is in the last leaf. It's a very, very efficient data structure and works really well for a lot of data types. It has a lot of good characteristics. B-trees tend to be very shallow compared to other tree structures, like compared to, say, a binary tree or a red-black tree. And shallow structures are good in databases because it means you have to go out to disk less to get as you walk down the index. It provides order log n access to leaf nodes, yay, not on. And it has a lot of good characteristics, like it's easy to walk in ordered directions, so it can help with order by, merge joins, and other kinds of operations that require ordering. Because Postgres has a large range of data types, and data types can be of variable length, B trees have a variable number of keys per node, and each value is copied entirely into the index, which means that larger values in terms of number of bytes means fewer keys per node, so deeper indexes. This is if you're going to index, for example, very large text fields, keep this in mind, is that each individual node, which is a fixed size, 8K minus overhead in typical Postgres, can only hold a fixed number of keys. So perfect, we're done. Indexing solved. Well, not so fast. First of all, one problem with B trees is the entire key value is copied into the index. So if you're indexing, 288K byte character strings, that's not so good. Indexes can use the toast system, which is Postgres' way of storing offline large values offline, but you generally want to avoid that because you're really going to hurt performance that way. It requires a totally ordered type, a type that supports equality, greater than and less than for all values. Not all types are totally ordered. And this becomes important as we look at other index types. Hash indexes, let's talk about those. Hash indexes were a long broken feature of PostgreSQL. They were finally fixed in Postgres 10, yay. It converts the input value to a 32-bit hash code and the hash table, and then stores those in a hash table, which points to buckets of row pointers. The hash indexes only support one operator, which is equality, but that's a pretty important operator. That's a very, very common thing to do. The indexes are much smaller than B tree, especially once you talk about large key values like large text fields and byteas and things like that. And if there are few collisions, access can be faster than on a B tree because it has to walk fewer pages. They're great for long values on which equality is the primary operation. URLs, long hash values from other algorithms, SHA-256 kind of things, stuff like that. GIST indexes. So first of all, the thing to understand about GIST is it's a framework, not a specific index type. It's a generalized framework to make it easy to write indexes for any data type. And what a GIST index does depends on the particular type being indexed. For example, let's talk about Cartesian coordinates. And we have a point, and we have a box, and we have another point. So what's the relationship in terms of operators between these things? Are these equal? Are they greater than or less than? It doesn't really mean anything for Cartesian objects, for objects on a Cartesian plane like that. But let's take the inclusion operator. That makes perfect sense, of course. That point is inside that box. That's really a point, even though it's a big green blob. So that does make sense. So the GIST, which stands for Generalized Search Tree, can be used for any type where containment or proximity is a meaningful operation. And actually, standard total ordering can be considered a special case of proximity, proof left to the reader. This is great for things like ranges, geometric types, text trigrams that aren't totally ordered, but containment or proximity do make sense for them. They're not as efficient as a B tree for classic scalar types, or for simple equality comparisons. So if you just have an int and there's no other reason to use GIST, B tree is probably the one you want. Next index type up is GIN, short for Generalized Inverted Index. Both B tree and GIST indexes perform poorly where there are lots and lots and lots of identical keys. And full text search, in the classic case, has exactly that situation. If you have Postgres or field, for example, in a corpus that includes the whole Postgres documentation, there's going to be a lot of entries for that, and you're going to end up with a very non-performant index. But GIN indexes handle this very well. Indexes are forests of trees. The GIN indexes organize the keys, normalize words into a B tree, and then the leaves of the B tree are lists themselves and pointers to rows that hold them. And it scales very efficiently for a large number of identical keys. It is and for full text search, indexing array members of JSON fields, things like that, this can be a very powerful index type. And onwards we go to SPGIST. SPGIST is a space partitioning gist index. It's not a very widely used type, which is kind of a shame because it's pretty cool. It's similar to GIST in concept. It's a framework for building indexes. It has a different range of algorithms for partitioning these spaces compared to classic GIST. And it's designed for situations where a classic GIST index would be highly unbalanced. And we'll talk more about those kinds of situations later in the talk. BRIN indexes. This is a relatively new addition to the Postgres index family. BRIN stands for block range index. B-tree indexes can be very large. It's not uncommon for the indexes of a database to exceed the size of the heap, the actual data. B-tree indexes are fully general. They assume we know nothing about the correlation between the index key and the location of the row in the table, which is usually, which in the most general case is true. We don't know anything about it. But often we do know. For example, a lot of tables are like log tables where new rows are being appended continuously, and you'll have a field like this created at timestamp default now, which are insert heavy, and they have monotonically increasing keys like serial primary keys, timestamps, things like that. And if the tables aren't update heavy, which move things around on the in disk, the key will be strongly correlated with the position of the row in the table. So there will be kind of this range of keys generally maps to this range of blocks. And BRIN takes advantage of that. Excuse me. BRIN, instead of a tree of records, records the ranges of keys and the pages that probably contain them. And they're much, much smaller than a B-tree index. And if the correlation assumption is true, it can be much faster to retrieve ranges, like get me all the orders from last year, than a B-tree could be. It's not good for heavily updated tables, small tables, or tables without this monotonically increasing key, though. So still keep B-trees around. Lastly, we want to talk about Bloom indexes. These are not very heavily used by applications in my experience, which is a shame because they only have one use case, but it's a very unusual, it's a very, very powerful use case. So Bloom filters are kind of like a hash, they're only different. They're most useful for indexing multiple columns at once, like a large number of columns. And they're very, very fast for multi-column searches, which is, for example, if you have multiple attributes expressed as its own column, for example, you might have a product catalog with 20 different attributes up for a particular product and a user interface that lets you search multiple selections of these. Very helpful for that. And they're a very small fraction of the size of multiple B-tree indexes, which would be the other way of doing this kind of searching. Okay, there's the collection of indexes. But now that we know that, how do we actually use these? So we'll talk about this as pragmatic concerns. So first, the decision you need to make is, do you need an index at all? Because indexes are expensive, and they slow down updates, they increase disk footprint size, they slow down backups and restores. There are lots of problems with indexes. So as a rough rule of thumb, an index will only help if less than 15 or 20% of the table will be returned in a query. So, and this is the usual reason the Postgres planner will not use an index, is because it thinks that a large number of rows will come back, and using an index won't be efficient in that case. It's important to have good planner statistics. For the planner to use indexes correctly, it needs good statistics. So make sure all the tables are getting analyzed and vacuumed. And consider increasing the statistics target for specific columns that have these characteristics. A lot of distinct values and more distribution than 100 buckets, which is the default statistics target on Postgres capture. UUIDs, hex hash values, tail entropy text strings are all examples of things that often need a larger range of planner statistics. But don't just jam up statistics across the whole table. The speed of analyze and the size of these statistics tables depends on the setting of the statistics target, the highest statistics target in a table, a particular table. And if you just set it to 30,000 across the whole database, you're going to really, really slow down analyze time. Here's an example on bad statistics. So let's say you have 100 billion rows and 100 buckets. The field is not unique, and but there are only 25,000 distinct values in this. And you do a select for a particular item. The planner thinks 1 million rows will come back and decided index isn't useful here. And in this case, setting statistics target higher, the statistics target higher will likely generate much better plans. Postgres uses multi-version concurrency control. Indexes participate in this, and indexes store every version of a tuple until vacuum cleans up dead rows. So if you have lots of dead rows in a database, in a particular table in your database, you can end up with really bloated indexes. There is an optimization called hot that helps, but it doesn't completely eliminate this. So this means that in the default case, index scans have to go back out to the heap to determine if a tuple is visible to the current transaction. Be careful about this. So it can significantly slow down index scans, or the planner may decide not to use indexes at all because they're just too bloated. So keep up on vacuuming. Postgres does have a nice optimization called an index-only scan. If we know every tuple on a page is visible to the current transaction, we can skip going to the heap. We can just bypass that extra check. And Postgres uses the visibility map to determine this. So if a planner thinks enough pages are completely visible, it'll plan an index-only scan, which is much more efficient. There's nothing you have to do to cause this. The planner handles this, but just make sure your database is getting properly vacuumed. Some index scans are lossy. It knows the tuples on the page will match, but it doesn't know exactly which ones, and there may not actually be any matches. This means it has to retrieve the pages and scan them again and throw away rows that don't match. This is what when you see in a plan, a bitmap heap scan and a bitmap index scan, that's what it's doing. And there's some index types that are inherently lossy, like BRIN and Bloom indexes are inherently lossy. It has to do this recheck every time. Postgres recently introduced covering indexes. Queries often return columns that aren't in the index predicates of the query. So you are retrieving rows that aren't indexed by scanning the index. That's probably more common than not. Traditionally, Postgres had to go fetch the tuple from the heap to get those values because, after all, they're on an index. Just looking at the index wouldn't help. Postgres 11 introduced non-index columns can be added to the index, and they're retrieved directly when the index is scanned. Very useful. Doesn't help on index-only scans, and remember, you're increasing on non-index-only scans. Excuse me, and remember, you're increasing the size of the index with each column you add. So be careful. So the question with all of this is, what index do I use, and when do I use them? One last couple more quick things. GIN indexes are very fast to query, but they're much slower to update than other types of index. And Postgres records changes in a separate posting area for performance reasons and updates the index at vacuum time. And this can result in a surprising spike of activity on heavily updated GIN indexes or it not using the GIN index at all efficiently. You might consider having a separate background process that calls GIN clean pending list, a function that manually cleans the pending list if the posting list, if you're heavily updating a table that has a GIN index. And lastly, let's talk about unique indexes. A unique index is one where only the key value can only appear once in the entire index. B trees support unique indexes. Frequently, applications will do optimistic insertion recover on an index conflict. They'll do it. They'll say, "I probably the index of the duplicate. There's no duplicate. Do the index, and if it gets back an error, it'll recover from that." There is an on-conflict clause that's semi-recent in Postgres on updates and inserts. On inserts that can make this much easier. But this can be a concurrency killer, so don't expect very high insertion rates on the face of conflicts because Postgres has to do locking to make sure that the unique constraint is maintained. And just to mention, exclusion constraints provide a generalization of unique, which is it's a generalization that says only one value that passes this comparison is allowed in the table. You can think of unique as a special case of that for equality. And these can be very helpful for non-B tree index types where you want to have things like only that no two things that overlap are inserted into this index. Okay, so let's talk about how you decide whether or not to use you use an index and which type you use. And so we have a decision tree, so there. What index? How do we decide what index to use in a particular situation? The first thing we need to do is gather some information. Typical queries on the table, the columns and data types and operators that are being queried, and including those in joins because indexes can help joins, and how many rows these queries typically return. How many rows does the query return? Does it typically return a large percentage of the table? This includes things that don't look like they would do row fetches but really do, like count star. If you're returning 50, 70% of the table, an index probably won't help. So don't create one just to do that. Consider instead refactoring the query, consider summary tables or other techniques just before trying to throw an index at the problem. Small tables that fit in memory usually don't need indexes at all, except if you need to enforce a constraint like the primary key constraint. Which column in a multi-predicate query? Which column is are you going to create an index on? Always start with the most selective predicate. So, for example, if one of them is being queried on a unique column that should be unique, that's the one to go for. That is look for the one that will cut down the number of rows being considered first. If the predicates individually don't cut down the results much, but they do so together, that's a good sign a multi-column index will be useful. But first, we'll consider the single column case. Is the column a small scalar, like int, big int, float, UUID, timestamp, datetime TZ? We'll talk about inet and char types later. Is the value a primary key or otherwise unique? Slide advanced issues. If so, use a B tree. That's your only choice. Is it monotonically increasing on a large, rarely populated table and the query is doing a range operation? So you're fetching like a date range from something like that. If so, that's what BRIN is really good at. Otherwise, use a B tree in this situation. If the index is primarily used to support an order by descending, you can create it as descending. Otherwise, just use ascending. Is the column a text field? It's a varchar, a text, or char. You know, if you're weird, don't use char. It's really not good for much. Always use varchar or text. Are you doing full text search, trigrams, or other kinds of fuzzy search techniques, not just literal equality? That's a trick question. We'll talk about those guys later. Is the data structured and prefix heavy, and are you typically doing prefix searches? URLs are a very good example here, because if they're full URI form with the access with HTTP or HTTPS, things like that, consider using SPGIST for this, because typically SPGIST handles very well if there's a very unbalanced space. For example, if you're typically looking for URLs, a prefix like Wikipedia might be very unusually heavy in it. So an SPGIST is very good for these kinds of spaces that are unbalanced near the beginning. Is the generally value small, or do you require total ordering? Are you going to do greater than and less than, as not just equality? Or are the values small? If so, B tree, because B tree is the one that gives you total ordering, and B tree handles small fields generally well. So if either of those are true, B tree is the one for you. Otherwise, consider a hash index for these because it'll handle equality and it will be more efficient than a B tree index for very large values. Is the column a byte? Why are you indexing a byte? Don't index a byte. There's no reason to index a byte. If you absolutely must index a byte column, either use hash or calculate a hash and store it separately, and then refer to the previous decision points about how to store the hash value. Is it a geometric type or a range type? GIST is here for you. That's what GIST does. PostGIST indexes are all GIST-based, so you just want to use those. If you need nearest neighbor searching, GIST for sure. For example, this is what's sometimes called in geoinformation systems the Starbucks problem, where you say, find me the 10 nearest Starbucks. And this is actually kind of a hard problem to solve in geometric information systems. But fortunately, Postgres has Postgres has a built-in index type, which PostGIST will use, that handles this very nicely. Experiment with SP just to see if it's good fit for your data distribution, because for some data distributions, especially things that are very unbalanced, there's huge clusters some places and very sparse elsewhere, SP just will handle it more efficiently. Is the column type inet? Well, are you? That's the internet type for internet addresses. Are you just doing equality? Just use B-tree. It's fine. You might try hash to see if it works better for your data set, but B-tree is probably fine. Are you doing prefix searches, which is very common, of course, in inet addresses, like you're looking for the class B address inside of a inet address? Consider SPGIST for this, because inet addresses are very heavily unbalanced. They very much favor some spaces over others, and SPGIST is very good for this kind of unbalanced searching, prefix searching. Is the column an array or a JSONB type? Are you just doing equality? Just use hash. Understand, of course, that equality needs to be fairly strictly defined here, because if you reorder the elements in an array, for example, it won't be considered equal under a hash operation or just standard equality. Are you searching for key values at the top level within the object? Use a GIN index. Unique key values from inner objects and a JSONB objects. You might consider expression B tree indexes, although GIN indexes now do support this. But often it's more efficient to extract them and use an expression B tree index instead. Is the column JSON without B? There is a separate type in Postgres, just JSON. Why is the column JSONB? You probably shouldn't be using that anymore. It's a very, very limited use these days. Really, an expression index is your only option here. Maybe hash if it's just strict equality. If you need indexing on a JSON column, it's much better to convert to JSONB. It has much better indexing capabilities. Are you doing full text search or fuzzy search? Full text search, create a TS vector from the text and create a GIN index on that, and you're done. That's what it does. You can either store that as a expression column, or a separate index, a separate column. Or use an expression index on that. If you store it as a separate column, you'll need to come up with a system to maintain it, like a trigger or something like that. Separate columns are better for complex TS vector creation, and frequently you append multiple TS vectors together, like the title and an abstract in the body and keywords and things like that. And for that, you probably want a separate column with its own TS vector. If you're doing fuzzy search, you can create an index on the column using the just trigram ops operator type, which is part of the PG trigram contrib package, and that does fuzzy search very nicely. Is there more than one column in the predicate? Postgres supports multi-column indexes. If the predicates together are highly selective, consider using a multi-column index. Just remember that an index on A, B, Postgres will almost never use it to search on B. I have once in a while seen Postgres used to search on B, but it tends not to be a very efficient search. So just assume that you can use it for searches on A and B together, or just on A but not on B. Find the right index type for each column individually and create an index based on the most selective column. Just remember that in an index, they all have to be the same type of index. So if the column requires a just index, but one of the fields is like as a scalar, like an int, you can use the btree gist package to get it gist operator for the basic scalar types. Is there more than one column in the predicate? Part 2. If the query pattern is an arbitrary combination equality comparison of various columns, consider a Bloom index. This is not uncommon for a GUI-based search filter. You go through and you have a web page that lists a bunch of attributes, and the user can fill in an arbitrary set of those. And that can be very inefficient using just standard B-tree indexes. If the predicates are selective independently, 2 indexes might be more efficient, though, than a multi-column index, so do test those possibilities. And does the query contain an expression? Well, Postgres supports expression indexes, where it indexes on expression rather than a static field. For example, you can an index on unaccent lower name instead of just querying on unaccent lower name. Don't forget that CI text exists for the lower problem, and CI text supports indexes just fine. And make sure that particular expression is heavily queried, because these are expensive to maintain. And if you index on a user-written function, just make sure it really is immutable. That is to say, it depends only on its inputs, not on the state of the database or anything outside of that. Just not declare that way. And remember, it can be surprising how many ways things can become non-immutable, like depending on the now function or time zones or things like that make a function non-immutable. Is one predicate highly selective? So, for example, where customer ID equals 12 and active, where only 10% of the orders are active, consider creating a partial index. You can create an index that only includes rows that include a particular Boolean predicate, and the index is much smaller and thus much faster to query. It only contains the rows that match the predicate, which is really nice. And you can really speed up index queries if your data matches this particular set. So here are some tools to use for indexing fun stuff. Do you need an index? PGStat user indexes, user tables, you can look for tables with a significant number of sequential scans. Not all sequential scans are bad, so look at the particular queries that are generating them. And you can also look in PG stat statements, the text logs, and processing your logs through PG Badger to find out how the queries actually are working. Is the index being used at all? PG stat user indexes keeps track of how many times an index is used. So look for ones that aren't being used and drop the indexes that are benefiting you. If your system's been running for 8 years and the stats haven't been reset and an index has never been used and you don't need it because it's not like a primary key index, drop it. Indexes have a large intrinsic cost of disk space and update insert time. Here's a URL to a query that we maintain that will show you unused indexes and give you suggestions on which ones to drop. Our index is bloated because indexes can suffer from bloat just like anything. Vacuum can't always reclaim space from indexes efficiently due to index structure. It's not as easy to reclaim space in an index as it is from a table. In the case of very frequently updated tables, it's worth considering periodic index rebuilds. Here's another script that checks index bloat, and very highly bloated indexes that are not being shrunk by where the bloat's not going down because of vacuum, it's worth it consider rebuilding them entirely. Our index is corrupted. It doesn't happen very often, but it does happen. You're getting errors during queries or bad results from queries. Postgres version 10 or higher has an amcheck extension that can do a basic check on index structure. The good news is these are easy to fix. You just drop and recreate the index. Version 12 has significant improvements to B-tree structure. Smaller indexes, especially if you have many duplicate keys, so that's worth upgrading for. It does require the index be reconstructed if it exists already, but you can build a new one and drop the old one. So, to conclude, indexes are great. Just remember they're an optimization. Always create an index in response to a particular query situation. Just don't throw a ton of indexes at a table and hope for the best. Experiment, test different index types to see what works. Postgres has a very rich set of index types. They're great. And pick the right index for the data. Don't go with B-tree by default. There are lots of different index types in Postgres. That's great thing to see. Monitor usage and size to keep the database healthy and happy. Check for bloat. Make sure the indexes are actually being used. And thank you for listening. And any questions? Okay, thank you very much. The moderator will be handing me questions, and I will be happy to answer any that you might have. So the first question, shouldn't we try to automatically create BRIN indexes to check to see if the column is BRIN friendly? It's an interesting idea. Right now there's no machinery in Postgres for changing what index type it is based on automatically. There's no real syntax or gears and levers inside of it to do that. There's also an evolutionary thing about using BRIN versus B-tree in that an index can be BRIN friendly at a particular moment in time, but then lose it over time. And so you may not want to have Postgres making that decision for you. But it's an interesting idea. You could certainly you might want to consider writing an extension that did that. Next question. Postgres can combine multiple indexes and do a bitwise and/or on them. This is just a nice bonus or something that plays a role in designing a schema. Well, it is a nice bonus, and you may want to consider that in terms of how you create your indexes. Specifically, do you need a multi-column index, or should you create two indexes, one on each column? The primary thing is, let's say we have a column A and B. If we do queries on both A and B independently, and then sometimes queries on both A and B, that would indicate that you would probably want to create two separate indexes and rely on the bitwise and/or to support that. If you only query on A and B together, then probably a multi-column index would be better. As to whether or not it involves creating the underlying schema, it depends on the data. I'm not. It's not immediately popping to mind, to be honest, about how you would drive a decision to create the columns as opposed to the indexes, varying between those two. But anything's possible. But yes, definitely in terms of index creation, you leaning on the and or functionality is fine. You definitely want to do that if the queries will support it. Thanks. Next question. Are SP just more expensive to create, store, update than GIST? Not particularly. They are of roughly the same cost. So if an SP GIST is better for your data, mostly when you have data that is heavily biased in one direction. That can be geodata that has very tight clusters of points and then very wide clusters elsewhere, or prefix heavy data. Then go ahead and play with an SP GIST and see if you get better results. Next question. Any trick about actually accessing the index tree in Postgres, displaying the index to leverage the structure of the index itself in B tree or GIST? There aren't any tools in Postgres itself that do something really nice, like dump it in a graphical format or something like that. That would actually be a pretty cool tool. Go write that. We'll be here. You can obviously use page inspect and things like that to get at the underlying data. What you probably want to do instead, though, is look at the data that's being indexed rather than the structure, and in terms of things like the cardinality of it, how many keys there are, and how the keys are distributed, and make the decision that way, rather than trying to look at the index structure itself. You can, of course, dump it using anything that will dump the underlying page system, page structure, or use amcheck, which is an extension in more recent versions of Postgres to check it. Those don't dump it in a graphical form. Those just show you the underlying bits. Next question. What kind of index is best for multi-autofield kind of query? Query which is used to auto-populate and comes with a like condition for multiple columns. That is a great question. This is a very hard type of query to optimize. You present the user. I'm going to make some assumptions here, so hope I'm right. That you present the user with a big form, and they can type in a set of fields to check one or the other. If these are equality, then you can use a Bloom index. Bloom indexes are very, very good at this kind of thing. If you're not using a Bloom index, then you may just and they're all prefix, or excuse me, if they're not equality, like they're ranges or that kind of thing, then you're probably saddled with multiple B tree indexes and hoping that the and or functionality will work out. It's very important to have good statistics in this case, and those are hard queries to optimize because you're throwing a very hard problem at the optimizer to settle it, to try to find optimal queries where there's where the query itself can change in a large number of different ways. I would look at a Bloom index and see if that'll work, though, because those can often be the right thing for these kind of multiple attribute queries. Next question. We had a situation where we could get a table scan on a query depending on what else was running on Postgres. When it was not busy, it used the index. I would have to have more data to actually answer that. The query optimizer doesn't look at the environment to analyze it, to decide what it's going to do or not. It doesn't look at, for example, what's in cache and what's not, or what memory is being used or what isn't. So nothing's impossible, but I don't know exactly what would cause the state of the system in that regard. One possibility, though, is that if the statistics had gotten out of date because of updates and inserts into the table, that could cause the query to go crazy because it didn't have the right set of statistics. And obviously, inserts and updates also result in a busy system. So that's one possibility of what could have happened there. Any other questions? Considering that fuzzy search is often unbalanced, would be interesting to have a SP just for PG trigram. Never tried it. Sounds really cool. Try it out and let me know. That being said, You definitely want to make sure that you can support the distance operator. And I don't remember right now if PG trigram in SPGIS supports the distance operator, because distance is kind of what it's all about when doing trigrams, you know, the arrows on 2n dash in the middle operator. So make sure that's supported. I don't remember, honestly, off the top of my head. If it is, give it a try and it may work great for your data. And any other questions? Last questions. Best index for in clause. Well, probably B tree. Depends on the types of the stuff in the in clause, of course, but probably B tree. That is a great leading question, though, and I don't know if you intended this way, but I'll answer it this way. Giant in clauses are going to start becoming problematic over, if you have 10, 20 things on an in clause, it'll probably still use an index. Once you get over 100, though, the chance of it using an index does go down a bit, as the planner has to work hard to decide if an index is valuable or not. And once you start getting these wacky in clauses that ORMs can create sometimes, like 1,000, 2,000, 10,000 entries in the in clause, it's going to be pretty hard to optimize that. You might want to consider finding out what's generating this giant in clause and using a join or a subselect instead. So. Okay, and I believe that's all the questions. Checking for moderator confirmation here. And yeah, and thank you very much. And I really appreciate you taking the time to watch.